right, now I'm going to go over how to classify a reaction. And usually when I teach this, I use the illustration of relationships. So you'll have to bear with these examples. They're a little corny. The very first type of reaction is called a combination reaction, or synthesis is usually the term we use for this. This is whenever you have two reactants and they come together to form one product. So your illustration is marriage or relationship, the two becoming one. So they're pretty easy to identify. When you have a reaction, you'll always end up with one product if it's synthesis. So an example of that would be when iron rusts. When it's left outside for a while, it turns into iron oxide. The iron and the oxygen synthesize, or they come together to make iron oxide. But you'll notice that the subscripts changed based on those charges, crossing the +3 charge from the iron, the -2 charge from the oxygen, and then we have to add coefficients to balance that equation. The second type of reaction is called decomposition. Decomposition is the opposite of synthesis. So whenever you have one reactant that breaks apart into two or more products, that is decomposition. So in our examples that I'm using, my illustrations, the example of this would be a breakup or divorce. You start with one thing, it splits up into two or more things. So my examples as far as chemicals go, this is the formula for hydrogen peroxide. And I don't know if you've ever noticed that hydrogen peroxide is usually stored in dark brown bottles. And the reason why is it is very sensitive to sunlight. So as soon as it's exposed to sunlight, it decomposes into water and oxygen. So if you've had a bottle of peroxide in your medicine cabinet for a while, it might be that it has already decomposed and it's mainly just water. So that's why you need to, it does have an expiration date and you need to replace it pretty often. Here are some other examples. Carbonic acid decomposes readily into water and carbon dioxide, and ammonium hydroxide readily decomposes into ammonia and water. So you'll notice that decomposition reactions isn't an even split. With this reaction, it didn't split into H2 and O2. It split into water and oxygen. Down here, this didn't split into H2 and CO3. It split into water and CO2. So it can be a little challenging to predict what the products are for decomposition reactions. The next type of reaction is single replacement, and this is where the relationship illustrations are going to get a little bit weird. What happens is you have a compound, so usually this is going to be a metal and a non-metal, and you have a single element. And what happens is that single element takes the place of something in the compound and sort of boots it out. So you can think of a relationship that's really happy, both parties are getting along well, and all of a sudden, we call this a homewrecker comes along and causes the couple to split up. So now one of the members of the couple is now single, and now we have a new couple. So some shady stuff happening here. In a real world example with chemicals, you can see that magnesium replaced hydrogen in the hydrochloric acid molecule. Hydrogen was released as a gas, so notice it's H2 on the right side of the arrow. Magnesium is now paired with chlorine, and notice, just like we learned with charges, that since magnesium is +2 and chlorine is -1, you have to cross the 2 and the 1. So we would, if this is not a balanced equation, if we were to balance it, we would put a coefficient of 2 in front of HCl. One more thing about this, you need to note that metals always replace metals and non-metals always replace non-metals. So in this equation, A is representing a metal, and that's why it serves as the cation on the right side of the equation. B is also a metal. Metal got replaced, and now it's by itself. So now we get to double replacement reactions, and for the sake of my illustration, this would be if two couples decided to switch partners. Really weird, but I have seen it happen. So you can see in this equation that you've got AB plus CD. So A and C end up switching places. Now C is with B on this side, and A is now with D. So notice if A and C are representing cations or positive ions, they are still serving that same purpose on the product side. They're still going to be cations. So in this example, this is actually how we neutralize acid. If you ever spill hydrochloric acid in the lab, usually what I do is I come behind you and pour a little bit of baking soda, which is sodium bicarbonate. I pour that on the acid, and those end up neutralizing each other. The first product they make is carbonic acid, and the other product is salt. Carbonic acid, as you saw a couple slides ago, this slide here, carbonic acid immediately decomposes into water and carbon dioxide. So, back to where we were, the products of that reaction are all harmless. You have water, carbon dioxide, and then salt. So that's why it's always best not to wipe up an acid with a cloth, but to neutralize it first with baking soda. And that question you will actually see on your test for this unit. I'll ask you, why do we need to neutralize acids with baking soda? And you'll need to prove your answer with this equation here at the bottom. So make sure you memorize this equation. But hopefully that makes sense as far as double replacement reactions go. The hydrogen and the sodium switch places. So now sodium is with chlorine, hydrogen is with CO3. And then our last type of reaction is combustion. So if you remember back in our Unit 4 lecture, we talked about organic molecules, and we talked specifically about hydrocarbons. We talked about alkanes, alkenes, and alkynes. Those are all types of hydrocarbons, which are just molecules made up of hydrogen and carbon. Those are going to serve as sources of fuel in a combustion reaction. And these are the reactions that catch on fire. Now, the only way you can burn an organic molecule is to have oxygen. So you'll notice that for these types of reactions, a hydrocarbon will be one of your reactants, oxygen will be your other reactant, and your products are always carbon dioxide and water, assuming that this is complete combustion and not incomplete combustion. Side note, if it were incomplete combustion, your product would be carbon monoxide. But these types of reactions are very easy to recognize. Like I said, the subscripts of the hydrocarbon might change, but the general structure will always be carbon and hydrogen, maybe oxygen in the formula as well. The other three parts of this equation are always exactly the same. So for this next slide, we're going to practice identifying these types of reactions. In this first example, you can see that there are two reactants and one product. So that is an example of a synthesis reaction. In our second example, this is the dead giveaway here is that aluminum is single on the left side, lead is single on the right side. So anytime you have something single on both sides of the arrow, that is a single replacement reaction. In this next example, we have 4 compounds, and you can see that calcium and hydrogen switch places to make water and calcium chloride. So this is a double replacement reaction, when you start with 2 compounds and you end with 2 new compounds. This next equation, this should look familiar. This is combustion. So this is ethane, and we are combining it with oxygen to form carbon dioxide and water. So that's combustion. And then lastly, you have one reactant that splits apart into two products. So that is decomposition.